go? Okay. Good morning, everyone. Welcome to Professional Development Seminar Series. I'm Tom Ravens, Professor of Civil Engineering here at UAA. The title of my presentation is Defining the Cost of Coastal Hazards, a First Step Towards Coastal Resilience. Co-authors of this presentation include Anna Miller and Ethan Hunstiger, who are both Master of Science in Civil Engineering graduates, recent graduates from our civil engineering program. So I'm going to start by giving a brief description of the situation that I see the rural communities, coastal communities are in. It's kind of bleak. They're sort of subject to some significant coastal hazards. The General Accounting Office has stated that 184 or 86% of Alaska Native villages are already impacted by flooding and erosion, and 4 are in imminent danger. And the Brookings Institute stated there is no adaptive governance framework in place to evaluate when communities and government agencies need to shift their work from protection in place to community relocation. In addition, the Interagency Arctic Research Policy Committee, IARPC, in their biennial implementation plan for the Arctic Research Plan, has sort of identified the development of maps for visualizing coastal risks as a priority, coastal risks of erosion, permafrost thaw, and flooding. And they want to generate those maps in order to, amongst other things, inform investments. So, which means making decisions, I think. So, as I see it, in that context, the overall research goal of our research network is to develop methodologies for quantifying and communicating Arctic coastal risks, accounting for climate change. And why do we want to do that? Because we think it will be of assistance to decision makers and planners. You know, if you think about that 184 communities on the Alaska coast, it would be just super helpful if we knew going forward a few decades what the anticipated cost of erosion would be, what would be the cost of flooding, permafrost thaw, etc., so that we can make really well-informed decisions about how to proceed. So the specific objectives of my talk today are really to predict the cost of coastal flooding and coastal erosion. Other things that are in the work are predicting the cost of permafrost thaw and salinity intrusion. So I have two primary parts of this presentation. The first one concerns predicting the cost of coastal flooding. I'm going to do that with two different methodologies. Methodology A is sort of a generic methodology, which is predicting the cost of road flooding, actually going to focus on just the flooding of roads, not all impacts of flooding, but focusing initially here on road flooding. And we're going to predict the cost of road flooding based on this unit cost of road flood exposure, which, thinking about it, is seeming like a reasonable way to go. We're going to sort of be able to check that methodology by adopting a second methodology, methodology B, where we estimate a cost of flooding based on computing the cost of flood mitigation, considering specific alternatives for mitigating the flooding. So all of this work is going to be focused on Hooper Bay, where we have a demonstration project. And then the second part of the talk, I'm going to shift to how do we go about estimating the cost of coastal erosion. And once again, I'm going to have two estimates or two approaches. The first one is actually just stating the approach of the Division of Geological and Geophysical Surveys. They have an approach based on estimating the infrastructure replacement costs. When they identify infrastructure impacted by erosion, they estimate the cost of that erosion based on the infrastructure replacement cost. And I'm going to introduce a second way we might go about estimating the cost of coastal protection. So we're beginning here with estimating the cost of flooding. In the left, you see the community of Hooper Bay during a 2016 storm. You have in Hooper Bay, this is, by the way, a mainland community. It just looks like a series of islands during this storm because of the flooding, right? But in Hooper Bay, you have a few community centers. This is Old Town, where they have a lot of infrastructure, including water wells and a sewage lagoon. And then you have Newtown. And then you have that airport access road. And then on the coast here, you have the airport. You can actually see the breaking waves during the storm. So this is a 2016 photo, and you can actually see the airport access road in the photo. And the reason why is because in 2016, this road was elevated like 6 or 7 feet or something like that. And this road elevation project is going to feature largely in this presentation. We're going to be concerned about how much it costs to raise the road and how effective that road was at mitigating flooding. So the community of Hooper Bay has a population of 1459. It's a low-lying community. It's right on the YK Delta. We already looked at a few of the features, but here's maybe a better view of some of the elements of Hooper Bay. You got the airport right here. You got that airport access road. You got Newtown, and then you got Old Town. So, and then you see Hooper Bay on the map of Alaska. Once again, on the YK Delta, on the Bering Sea, low-lying community. Actually, the average elevation of the YK Delta is about 2 meters above mean sea level. So that whole area is vulnerable to flooding. So the middle panel in the upper row gives some information about historic floods and flood elevations in Hooper Bay. In the lower left, you see that photo again of the 2016 flood event. But what I want to emphasize is how much infrastructure is really vulnerable to flooding in Hooper Bay. The airport gets flooded. The airport access road used to get flooded. It will eventually with sea level rise. It's currently not typically getting flooded. Houses are getting flooded. Buildings. Actually, in Merbach, the recent storm, 3 houses got lifted off their foundation, and a tank from the tank storm floated away. So it's very much vulnerable to flooding. There's also a power plant in Old Town and a water plant, which are vulnerable to flooding. So to sort of get a handle on this exposure to flooding, we've developed this flood model. So you can see in the upper right a depiction of flood depth in Hooper Bay during the 2005 storm, which is something like a 14-year storm. This is a computer-generated simulation using Delft 3D software. And I know you can't really see the flood depths, but red is something like knee to ankle deep, and yellow is ankle to hip deep, etc. And in the lower right, we sort of imagined what happens if that 2005 storm happens in 2050 when you have a 30-centimeter sea level rise. Of course, it's going to be more impactful. So these flood projection tools are useful for various purposes. Summit Engineering has been working on relocating the sewage lagoon which is right here. The projected or planned location is there, and these simulations sort of demonstrate that it's likely that that new location for the lagoon will not be flooded, at least in a 30-year time frame. These flood simulations are also going to figure prominently in the work that I'm going to talk about now about estimating the cost of flooding. So if you remember, I was going to talk about or introduce two methodologies for estimating the cost of flooding. This first one is basically a generic approach. There's a 4-step procedure here. First, we develop a coastal flood model for Hooper Bay, and I've actually showed you some output from that model. And we use it to simulate 9 historic storms, the largest historic storms between 1992 and 2011. The second step will be to compute the annual flood exposure, which has units of kilometer hours per year. We're going to be talking about that quite a bit. We're going to compute the annual flood exposure for that section of road for which a flood mitigation project has been conducted, that road, airport access road, and for which cost data is available. This annual flood exposure accounts for the length of roads flooded and the duration of the flooding in a typical year. The third step will be to develop this unit cost of flood exposure, which is going to be the ratio of the flood mitigation project, the airport elevation project, relative to the annual flood exposure of that road segment that is mitigated by that project. The fourth step will be to make use of that unit cost of flood exposure to project community-wide flood risk into the future. And the equation for doing that is shown there. And I'm going to go through each of these 4 steps in detail, so you don't have to memorize it, okay? It's not going to be a test. I'm going to give you the answer. So the first step was developing the storm surge model and the flooding model. And rather than reinvent the wheel, we made use of an existing Corps of Engineers ADCIRC model. So this figure shows the extent of that ADCIRC model, as well as the bathymetry used. The resolution of this course grid model is something like 5 kilometers. We used the output of simulations of historic storms that the Corps did to drive a high resolution coastal model. So this high resolution coastal model domain is right here. It covers an area 150 kilometers by 200 kilometers. The resolution in this domain, this coastal domain, is 170 meters, meaning every 170 meters you have data on flood depth. And then where you see this little square, that's basically Hooper Bay. And there we have actually even higher resolution to 20-meter resolution, which really gets to the scale where you can really understand the distribution of flooding and flood depth. So first thing to know about models and modelers is that they're not trustworthy in general, right? So you have to make sure that the model calculations are reasonable, and you do that by comparing them with observations of some type. So on the left here, we have a comparison of flood height during the 2011 storm at Nome. We're comparing model generated flood height to observations at the tide gauge there. We also have some validation of the coastal model accuracy. We don't have a good gauge there like they do at Nome, but fortunately the DGGS analyzed historic photos and estimated storm heights from some of the prominent historic storms. And we've compared our model generated storm heights to the photos, and we find that our calculations are within 0.5 meters of what the photos indicate. Also, community members have said that the flood extents in particular simulations are reasonable. So we have, it's not perfect, but we have confidence that this is a reasonable model. So as I mentioned in that step one, we got to generate the model and simulate 9 historic storms. So these are the 9 largest storms between 2011 and 1992, and they're ranked from largest to smallest according to peak surge height. So we did extremal analysis, and in particular used a Weibull distribution to determine the return period of these storms. So for example, the largest storm, the 2005 storm that I showed simulations for earlier, according to this analysis, has a return period of 17 years, meaning a storm of this magnitude producing this height, this level of flooding would happen on average about every 17 years. So we've finished step one, and so now we're into step two, where we're going to compute the annual flood exposure. And going to go into detail about what this annual flood exposure is really all about. So the end result, we're going to come up with this annual road flood exposure in units of kilometer hours per year. The first step to get there is to compute the flood exposure of individual road segments to historic storms, focusing on those 9 historic storms. And in order to define this exposure in kilometer hours of flooding during individual storms, we designate these observation points. So in the lower left, you see a map of Hooper Bay, and we have a number of different observation points identified. Each observation point is representative of a certain length segment of road. So for example, 1, 2, 3, 4 are right on the airport access road. So the type of data that we have from the model is shown in the lower right. These are time series of flood depth during the 1995 storm at the observation points 1 through 7. So hopefully you can see how we can get the flood exposure from these individual storms. You guys good with that? Number of kilometers flooded and the number of hours flooded, focusing on individual observation points and then summing it all up. And then the next step is to actually compute the annual road flood exposure, AFE, which is a weighted average of the flood exposures from the storm, the individual storm exposures. So the equation is to the right here, and we say it's a weighted average. What does that mean? Well, what we mean is that storms that happen fairly frequently, like a 2-year storm, will be given a much higher weight in the overall average than a storm that happens very infrequently, like a 17-year storm. So we got this annual flood exposure, and we actually calculated it for a section for that airport access road. Essentially before and after the flood mitigation project, to show how much the flood mitigation project reduced the annual flood exposure. So our third step is then to determine the unit cost of flood exposure, which is the ratio of the cost of the flood mitigation project to the annual flood exposure of the road section that was where the flooding was mitigated. So again, we have more detail on that. So the annual cost of the airport road flood mitigation project, the raising of this airport access road, was $8 million. And since it had a 30-year design life, the annual cost was $267,000 per year. With the flood modeling, we computed the annual flood exposure of this particular airport access road to be 9.6 kilometer hours per year. And so this led to this unit cost of flood exposure, $27,900 per kilometer hour. So it's a little bit funny. You guys can tell me what you think about it at the end. But I think it's appropriate because it allows for relatively straightforward estimates of flood risk. And that's what we do in step 4. So in step 4, we take advantage of this unit cost of flood exposure that we've calculated. In step 4, we're interested in computing the community-wide flood risk for the 2020 to 2050 time period. And the way we do that is we use that unit cost that we just determined, and then we calculate the annual flood exposure, average annual flood exposure for 2020 to 2050. And the product of those two is giving us the flood risk for Hooper Bay for all the roads between 2020 and 2050. And so this is the math. We had determined the unit cost to be $27,900 per kilometer hour. The average annual flood exposure between 2020 and 2050 was 16.7 kilometer hours per year. And that gave us that $465,000 per year as a flood risk for Hooper Bay between 2020 and 2050. If you take that annual rate and multiply by 30, you get $14 million. So that's our first estimate of the cost of flooding in Hooper Bay, $14 million for the time period 2020 to 2050. And going a little bit into the details here, that annual flood exposure that we calculated, the 16.7 kilometer hours per year between 2020 and 2050, is basically an average of the annual flood exposure for 2020 and the annual flood exposure for 2050. We got the annual flood exposure for 2050 using the same procedure that I outlined, except we simulated each of those 9 historic storms, assuming a 30-centimeter sea level rise. So we're going to move to methodology B. Methodology B, we're going to make use of that flood model. We're going to use it to design 3 alternative approaches to mitigate flooding. First approach is raising the elevation of the roads that are flood prone. So we need to know how high the flood is in order to figure out how high to raise the roads. That's the first alternative. The second alternative is to build a roadside dike to prevent flooding of the roads. And that's a roadside dike around Old Town. You'll see why in a second. And then the third approach is to build a large regional dike. And there's some advantage to that because you're generating big areas that are safe from flooding, we think. So all of those objectives require that we simulate these storms for the 2050 period. And this is just giving you a flavor for what the flood depths would be like in the year 2050 for the community of Hooper Bay. So this is actually the peak flood depth for considering all the big storms, assuming that they happened in 2050 with a 30-centimeter sea level rise. And one of the things that's noteworthy, I believe, is the flood exposure of Old Town. You can see this ring road around Old Town is essentially flooded. In addition, the connection road between Old Town and New Town is also flooded. So now I'm going to give you a little bit more information about those 3 alternatives that we considered for flood mitigation. So there was basically 3 stretches of road in Newtown that needed to be elevated to prevent flooding in 2020 to 2050. In Old Town, you need to elevate the whole rim road, essentially. And you also need to elevate the road connecting Old Town and New Town. Alternative 2 involved building this roadside dike around Old Town. So rather than raise the elevation of the roads, we thought, well, why don't we just build a dike around the whole, that sub community, if you will. We still have to raise the individual roads in Newtown, as well as the road connecting Old Town and Newtown. But it is an alternative that we explored. And the third alternative was to build these regional dikes. And so you can see these are the dikes, and the two dikes basically protected you from the west and the east. You still had to raise those three road segments in Newtown. So this is a summary of the costs that we calculated for these different alternatives. So the first row is the no action alternative. Like you do nothing. You say we're not gonna deal with this. There's no cost at all, right? But you do have to experience a lot of flooding. Basically, it's 19.8 kilometer hours per year of annual flood exposure if you do nothing. Now, with the generic flood risk approach, the unit cost approach that we developed with methodology A, we got 14 million. And now we have the three additional alternatives. What we see, what jumps out at me is the fact that the generic flood risk approach seems like it overcalculated the flood risk when you compare it to the analysis of the three alternatives. But when we looked into it, we realized that when we were calculating the unit cost in order to do this generic flood risk calculation, we had included the setup and overhead costs, which amounted to 3.6 million. And for whatever reason, when we were thinking about the alternatives, those three alternatives, those specific alternatives, like elevating the roads individually, we basically imagined this is going to be a community-based effort, and there would be relatively little in the way of setup and overhead costs. And that explains a lot of the difference there. So the final row is the relocation costs. So there's been a number of communities who have produced estimates for relocation, including Newtok, Shishmaref, and Kivalina, and basically prorating those estimates, accounting for population, we get 272 million for Hooper Bay. And so what you see right away is, well, it's relatively cheap to mitigate the flooding compared to relocation. So that's why they're not relocating, right? Of course, that's not everything you have to do. You also have to mitigate erosion and some other stuff, right? So in my view, this work demonstrated a simple but realistic way to estimate the risk costs of road flooding in Alaska coastal communities. The comparison of methodology A and B indicates that the results are reasonable. With some additional thought, I believe this approach could be expanded to estimate the cost of flooding of other types of infrastructure. And also we can broaden the application and go, cover all of YK Delta or all of Western Alaska with this approach, just to get an idea of what is the flood, what are the flood costs that we're anticipating in the next 30, 60 years. So the second part of my presentation, if you guys have any if you're jumping up and down with questions in your mind, I'm willing to entertain a question now or two, if the organizers let me do that. But otherwise, I'll move on to part two. Okay, here's a quick question.
It looked like most of your options there are pretty close to the $8 million cost of just what I think you had some real numbers on what the access road to the airport that cost. Was that not about $8 million as well to elevate it? You said 6 feet.
Yeah, it was 8 million. Yeah.
So it just seems like, I don't know, just kind of an observation that's real close to a lot of what your different mitigation measures and alternatives ended up being.
Yeah.
3 or 4 of them.
Right.
Costs as far as you have some real cost numbers for that, and these are obviously projected using your methodologies. But so it seems, I agree with your conclusion. Obviously, a lot cheaper than relocating when you're looking at the order of magnitude there. But they're really close together, so I guess you'd have to look maybe at some other factors to try to decide which
Right.
one of those you might want
Yes,
to land on.
yes, yeah, that's right. Community preference, right?
Question,
Sure.
what did the dike look like? Is it just rock material or
The dike was built very much like that road I showed you.
the road
So-
started functioning like a dike as well?
Uh,
This is different.
The roads do function like dikes, yes. But when we built the dikes, we didn't make them so wide as the roads, because roads have to have, a couple lanes of traffic, right? So I think when we designed the dikes, they looked a lot like the roads, except they were not as wide.
Do they have a good gravel source and riprap nearby, or is that all imported from some distance when they had to do that?
That is a good question, and I don't know the answer. But the costs for all the materials are ones that are real, because basically we got them from this road elevation project, the 2014, 2016 road elevation projects. So we looked at the compilation of bids and
How did you determine the elevation to set the road at? Is that like based on the 10-year storm surge or?
so it was based on this annual the exposure, flood exposure calculation. So we raised them up so that that particular segment would not contribute to, and so basically the definition of flooding, and I should have said this earlier, is when the water depth is greater than 4 inches or 10 centimeters. And so we would raise the elevation of the road so that essentially there would be no flooding up beyond 4 inches in that road segment. Same for the dikes. And so, and these structures are kind of like trapezoidal, right? So the taller they are, the more material you need to include. So that's how they were able to use the output from the model very effectively to basically say how much material you're going to need to build this dike or to build these or to elevate these roads.
Which storm generated that 4-inch water surface flooding elevation?
Well, it was probably the 2005 storm, right? That was the biggest one.
So there's no like criteria that it's a specific frequency or duration.
Sorry?
There's no criteria that says it has to be like a 2-year storm or a 10-year storm.
Yeah, we didn't go that way. That could be it. That would be another way to do it, right? The sort of premise, the hypothesis is that flood exposure is going to drive efforts to mitigate the flooding. And so, and the flood exposure is also going to drive the cost of flood mitigation. And that's where that sort of unit cost sort of concept came from. Like how much it costs to mitigate a certain amount of flooding, the flood exposure. So I'm very curious to, have follow-up conversations, because maybe there's a better way to do this. This seemed reasonable to us. So thank you for all those questions. I guess maybe there's no online questions, at least no one's shouting at me that there are. So I think we can go to the next part of the presentation, because it looks like we have enough time. And that is, how do we estimate the risk or cost of coastal erosion at Hooper Bay? So this is a photo showing these interlocking concrete blocks, which is part of the coastal protection effort from the 1980s. And this particular figure is coming from a Corps of Engineers report after the October 2004 storm. And you can see it got ripped up pretty well. And this photo is not too far from the airport, which is where the erosion risk is the greatest. In fact, this figure shows the coastal erosion hazard in Hooper Bay. This is a figure from DGGS, and it's the north end of the airport that is seeing the biggest coastal erosion threat. There, the erosion rates historically have been 5 to 8 feet per year. Another area of concern in Hooper Bay is right over here. There's a slough that comes really close to Old Town, and there's erosion happening there as well, or projected erosion. So in I forget what year it was, but I think it was in the 90s, when they realized the interlocking blocks weren't really working, they upped the ante and built this sheet pile wall that you see here to protect the northern end of the airport. What you also see in this photo is that, and you can't see it so well, I apologize for that, but there's like asphalt and sort of other hard debris that was sort of placed on the toe of the sheet pile wall. Over here, maybe you can see a little better, they're actually using some of those, recycling some of those concrete blocks from the 1980s effort. And one of the things that you want to do if you're building a coastal structure is you want to protect the toe, because the way coastal structures feel is if there's scour at the toe of the structure, then the whole thing can topple over. So the key thing for any kind of seawall, such as this sheet pile wall, is to armor the toe of the structure. So, and this is sort of done sort of ad hoc. And so in that same 2014 to 2016 project where they raised the elevation of the road, they also went back and sort of improved the scour protection of the toe of that sheet pile wall. They built basically a 413 foot long rock revetment. I don't have a picture of it, but the standard rock revetment that the Corps designs is this, so shown by the schematic here. And those rocks would be really boulders. They would be something like 3 or 4 feet in diameter, I guess, because you have a pretty significant wave climate out there in the Bering Sea, maybe even bigger. So this is, I think that for me, let me just take a break here, shut off my phone. Excuse me. So this figure is sort of just recapping some of the information I've just presented, but giving you the spatial location of these structures. So the sheet pile wall, the 1,000-foot sheet pile wall is protecting is shown in green in this figure. And the rock revetment that they put in 2014 to 2016 is shown in the red dashed line. And what you see is that the sheet pile wall extended well beyond the rock revetment. DGGS has provided this shoreline change forecast for Hooper Bay. I believe it's based on linear interpolation or linear projection. And you maybe can't see it really well. I should have this blown up, but this area just below the erosion protection area that is essentially referring to that 2014-2016 project is definitely subject to, in this figure, is projected to be subject to erosion, significant amount of erosion. And in fact, there's an additional 461 feet of linear feet of runway that will be subject to erosion in the 2023 to 2055 timeframe, according to those DGGS projections. And so now we're going to get to the cost estimation approach. So DGGS sort of I thought provided really great service to the state by using these erosion projections as a basis for estimating the cost of erosion. What they did was they basically looked at, in this case, how many linear feet of erosion, of how many linear feet of runway would be impacted by erosion, projected erosion, and then determine the replacement costs of rebuilding that runway if it was impacted by erosion, and use that as a sort of a cost estimate. So this is just coming from their report pretty much. So in the time frame 2035 to 2055, they projected 463 linear feet of runway would be impacted by erosion. And then ANTHC gave DGGS some estimates of the cost of replacing airports. And based on that information, they came to a cost of 4.6 million to estimate the cost of replacing the airport runway impacted by erosion in the 2035 to 2055 period. So I think that is the first estimate that I'm sort of presenting here. And when we looked at it, and this is in particular Ethan Hunstiger's work, we thought about it from the point of view of, well, the actual cost of erosion is really the cost to mitigate, to protect the infrastructure, to mitigate any erosion. And so basically we saw this 460 linear feet of runway, and we thought, well, what's really going to happen to protect against erosion there? Well, they're just going to extend this rock revetment that they had already built to protect the toe here. They'll just extend it. That's 460 feet. And so we used the costs from the 2014 to 2016 project to determine that the cost of building that revetment is $5,200 per linear foot. And then we use the 463 feet of exposed runway that was projected by DGGS to arrive at a cost of erosion of 2.4 million, which is obviously significantly below the 4.6. But it's obviously it's a different estimate, but I'm suggesting that maybe this 2.4 is more realistic for what the short-term cost of erosion will be as far as mitigating the threat to the airport. So the conclusions from this section of the presentation, in my view, are the DGGS presented, developed this cost of erosion based on estimating the cost of replacing infrastructure impacted by erosion. They came to 4.6 million for the airport in that 2035 to 2055 timeframe, or 2023 to 2055. We went and looked at it with the second estimate approach, arriving at the cost of protecting against erosion would actually be a little bit lower, it'd be 2.4 million. It turns out that so these calculations suggest that it's going to be less expensive to protect the existing infrastructure rather than to rebuild it somewhere else. And this general finding is also what I've read in a recent IPCC report. I think when people look at the economics in this situation, very often, this very valuable infrastructure behind the shoreline, and it's relatively inexpensive just to defend, to arm the coast, rather than lose very valuable land. Yes.
Is the 4.6 million to totally rebuild a runway somewhere else in the community?
I think that's how they estimated, yeah.
And from your earlier slide, it looks like it's getting erosion on the top of the slide, the north end. But if it's another option, could you just extend the runway further to the south? It looked like there's real estate down there that wasn't impacted by the erosion forces. That maybe as another alternative that might be even cheaper than either of those if you just needed an extra 400 or 500 feet on the south end and let the top end away.
Sure, that's definitely something to consider for sure. I'm not sure if, I know this, it definitely looks like there's some lakes, so you'd have to, there's a fair amount of filling, but it would be.
Right. There's one small lake there by your turnaround. And
Yeah.
it looked like you'd have another, I don't know, before you got to the larger lake, considerable distance possibly to extend it without having to rebuild the whole runway and just a partial reconstruction and a less erosion. Of
Right.
So
Especially since it seems like you got a little bit more wiggle room. You know, the orientation of the runway is such that you're moving away from the coast as you move south. So you got a little bit, that's right. There's another feature that's very interesting in Hooper Bay that I didn't talk about. It's the so-called salient. And this figure doesn't show it really well, but there's this accumulation of sediment offshore. You know, there seems to be transport from the north on the north side and transport from the south. And so it's sort of sediment is accumulating in this transient, and the whole transient has been slowly moving northwards. And so that's another factor that sort of that may actually, in the short term, reduce the erosion threat and actually reduce the cost of erosion, but we didn't take that into account here. Is there any comments or questions from online folks? Not sure. So that's basically what I have. I have like a whole nother presentation, but it sounds like you know, we did enough today, right? The other thing that I've personally been working on is developing predictive shoreline change models, in particular in the Arctic areas, the areas affected by permafrost and permafrost thaw. So that is sort of like those types of process-based models, as well as other approaches, can be used instead of the linear extrapolation that that DGS used to predict shoreline change. Yes.
So what was the deal with the core, the interlocking blocks? Why were those such a failure? What happened there? Was it just a blanket that covered the?
Yeah, it seemed, but maybe they were just, looks like they were too small. Because I know in, you know, in Galveston, Texas, which is, you know, similarly impacted by storms, they have similar interlocking concrete blocks, but they're much, much bigger. And so I sort of wonder whether they just were too small. I'm not sure why they failed. Seems like, you know, in general, there's a lot of trial and error to coastal protection, right? You try something out, either works or it works a little bit, and you learn from that, and then you try something else out. In fact, that's like the whole history, especially in the Arctic, right? There's a company, Coastal Frontiers, has been building coastal protection in the Arctic, especially for the oil companies, right? So, and it seems like that's how they do it. They basically just, a lot of it is just trial and error, and eventually over time they see what really works. And this
do a lot
stuff
of modeling too there with Coastal Frontiers. They have a site there at Oregon State University, a wave tank that they can model different storm surges, as well as one in Austin, Texas, at University. So in the case of North Star Island, which Coastal Frontiers was involved with that, they used a larger link concrete mat protection, and it served other purposes too, as far as ice riding up on the island, and creating a rubble pile to protect the North Star Island, but they were getting more and more storm surge as the Arctic ice pack went further out. You have a farther fetch distance, so the storms in the fall were bigger. So they did a lot of modeling, and they came up with kind of a linked concrete mat, which is a significant investment, but you have 3 or 4 foot by 4 foot concrete mats that are linked together rather than smaller interlock blocks that you saw there in that other. So depending on what you're trying to protect and what your resources available are, if you do the right modeling, you can come up with some different solutions. A lot of it is trial and error just to see what happens unless you have a lot of resources like the wave tank to test out your theories.
Do they barge them all up there, or do they? Plant
They
out?
precast them, I believe, up at Dead Horse, and then brought them out to the island, which is 8 miles offshore. And then they can truck them out in the winter. Of course, they have a nice road. So.
You should come and give us a presentation.
I'm not the expert on, but I know who you're talking about. Close friend of Terry's, Craig Leadersdorf.
Yeah.
And,
Yeah,
they're really good in what they do there.
yeah,
They're located down in California, but they've done a lot of design on some of the northern islands.
Yeah.
Pretty successfully.
yeah.
So is this gonna get funded? Are they gonna do that? Is that the Corps of Engineers that's gonna extend the revetment, or is it something being looked at by ANCHC?
Well, I'm not sure. Where that's at. To talk to, do you know Leif Thomas?
Mhm.
He works at the Corps now.
Mhm.
I actually ran into him at the Alaska Forum on the Environment.
Oh, yeah.
He's actually in charge of the seawall project up there at Utqiagvik. So if you have questions, ask Leif. 4 questions. We got an insider now. Great. So I guess that probably will conclude our talk. So thank you all for all the great questions. It's interesting when you give a talk. I gave this presentation to Alaska Forum on the Environment, and I got certain types of questions, and I give it to engineers, and they got different questions. So it's very interesting. So thank you.
What were they asking?
So one person asked me, what was the elevation of Hooper Bay? And it was a person who lived in Hooper Bay. Another person was asking me about the wind speeds and directions. What was the direction of the winds? And those are the 2 questions I can remember.
Were there a lot of people there?
There was more than 4 people. No, there was probably about 40 people in my session. Yeah.
Was there a lot of talk about Merbach?
I suppose there was in other presentations may have dealt with the Merbach.
I was up there right before. I ran into Jackie Overbeck.
Oh, really?
Like going on somewhere.
Oh, really?
Yeah,
Just
I was
before
stuck in-
Merbach?
Yeah, I was stuck in Bethel.
Right, 'cause
I was supposed to go out to Young Bay.
Okay.
Never made it.
Okay. Yeah, that's what when she sent some emails out saying something like, she was not in, normally she's very active in the emails chatter, right, about these storms, but she was very quiet because she was out hunting.
Yeah.
And so then when she got back, she went into gear. But it's funny that you ran into Jackie.
Yeah, we just crossed paths really quick.
Okay.
Thank you very much, Dr. Ravens.
Okay.
For the Qualtrics survey.
This
Oh yeah,
gentleman.
coastal is the
Coastal.
password for today's survey. All right.
Coastal.
Yeah, all lowercase.
Thank you.
That's another thing.